Fluid mechanics is the branch of physics that studies the mechanics of fluids and the forces on them. Fluid mechanics has a wide range of applications, including for mechanical engineering, geophysics, astrophysics, and biology. Fluid mechanics can be divided into fluid statics, the study of fluids at rest, and fluid dynamics, the study of the effect of forces on fluid motion. It is a branch of continuum mechanics, a subject which models matter without using the information that it is made out of atoms, that is, it models matter from a macroscopic viewpoint rather than from microscopic. Fluid mechanics, especially fluid dynamics, is an active field of research with many problems that are partly or wholly unsolved. Fluid mechanics can be mathematically complex, and can best be solved by numerical methods, typically using computers. A modern discipline, called computational fluid dynamics, is devoted to this approach to solving fluid mechanics problems. Particle image velocimetry, an experimental method for visualizing and analyzing fluid flow, also takes advantage of the highly visual nature of fluid flow. Brief history. The study of fluid mechanics goes back at least to the days of ancient Greece, when Archimedes investigated fluid statics and buoyancy and formulated his famous law known now as the Archimedes principle, which was published in his work on floating bodies, generally considered to be the first major work on fluid mechanics. Rapid advancement in fluid mechanics began with Leonardo da Vinci, Evangelista Torricelli, Isaac Newton and Blaise Pascal, and was continued by Daniel Bernoulli with the introduction of mathematical fluid dynamics in hydrodynamica. Inviscid flow was further analyzed by various mathematicians, and viscous flow was explored by a multitude of engineers including John Leonard Marie Poiseuille and Gottlieb Hagen. Further mathematical justification was provided by Claude Louis Navier and George Gabriel Stokes in the Navier-Stokes Equations, and boundary layers were investigated, while various scientists such as Osborne Reynolds, Andrei Kolmogorov, and Jeffrey Ingram Taylor advanced the understanding of fluid viscosity and turbulence. Main branches. Fluid statics or hydrostatics is the branch of fluid mechanics that studies fluids at rest. It embraces the study of the conditions under which fluids are at rest in stable equilibrium, and is contrasted with fluid dynamics, the study of fluids in motion. Hydrostatics is fundamental to hydraulics, the engineering of equipment for storing, transporting and using fluids. It is also relevant to geophysics and astrophysics, to meteorology, to medicine, and many other fields. Hydrostatics offers physical explanations for many phenomena of everyday life, such as why atmospheric pressure changes with altitude, why wood and oil float on water, and why the surface of water is always flat and horizontal whatever the shape of its container. Fluid dynamics is a subdiscipline of fluid mechanics that deals with fluid flow, the natural science of fluids in motion. It has several subdisciplines itself, including aerodynamics and hydrodynamics. Fluid dynamics has a wide range of applications, including calculating forces and moments on aircraft, determining the mass flow rate of petroleum through pipelines, predicting weather patterns, understanding nebulae in interstellar space, and modeling fission weapon detonation. Some of its principles are even used in traffic engineering, where traffic is treated as a continuous fluid, and crowd dynamics. Fluid dynamics offers a systematic structure, which underlies these practical disciplines, that embraces empirical and semi-empirical laws derived from flow measurement and used to solve practical problems. The solution to a fluid dynamics problem typically involves calculating various properties of the fluid, such as velocity, pressure, density, and temperature, as functions of space and time. Relationship to continuum mechanics. Fluid mechanics is a subdiscipline of continuum mechanics, as illustrated in the following table. In a mechanical view, a fluid is a substance that does not support shear stress. That is why a fluid at rest has the shape of its containing vessel. A fluid at rest has no shear stress. Assumptions. Like any mathematical model of the real world, fluid mechanics makes some basic assumptions about the materials being studied. These assumptions are turned into equations that must be satisfied if the assumptions are to be held true. For example, consider a fluid in 3 dimensions. The assumption that mass is conserved means that for any fixed control volume, enclosed by a control surface, the rate of change of the mass contained is equal to the rate at which mass is passing from outside to inside through the surface, minus the rate at which mass is passing the other way, from inside to outside. This can be turned into an equation in integral form over the control volume. Fluid mechanics assumes that every fluid obeys the following: conservation of mass, conservation of energy, conservation of momentum. The continuum hypothesis, detailed below. Further, it is useful at low subsonic speeds to assume that a gas is incompressible, that is, the density of the gas does not change even though the speed and static pressure change. Similarly, it can sometimes be assumed that the viscosity of the fluid is zero. If a fluid is viscous, and its flow contained in some way, then the flow at the boundary must have zero velocity. For a viscous fluid, if the boundary is not porous, the shear forces between the fluid and the boundary results also in a zero velocity for the fluid at the boundary. This is called the no-slip condition. For a porous media or otherwise, in the frontier of the containing vessel, the slip condition is not zero velocity, and the fluid has a discontinuous velocity field between the free fluid and the fluid in the porous media. Continuum hypothesis fluids are composed of molecules that collide with one another and solid objects. The continuum assumption, however, considers fluids to be continuous. That is, properties such as density, pressure, temperature, and velocity are taken to be well defined at infinitely small points, defining a rev at the geometric order of the distance between 2 adjacent molecules of fluid. Properties are assumed to vary continuously from one point to another, and are averaged values in the rev. The fact that the fluid is made up of discrete molecules is ignored. The continuum hypothesis is basically an approximation. In the same way planets are approximated by point particles when dealing with celestial mechanics, and therefore results in approximate solutions. Consequently, assumption of the continuum hypothesis can lead to results which are not of desired accuracy. However, under the right circumstances, the continuum hypothesis produces extremely accurate results. Those problems for which the continuum hypothesis does not allow solutions of desired accuracy are solved using statistical mechanics. To determine whether or not to use conventional fluid dynamics or statistical mechanics, the Kinesin number is evaluated for the problem. The Kinesin number is defined as the ratio of the molecular mean free path length to a certain representative physical length scale. This length scale could be, for example, the radius of a body in a fluid. Problems with Kinesin numbers at or above 1 are best evaluated using statistical mechanics for reliable solutions. Navier-Stokes equations. The Navier-Stokes equations are the set of equations that describe the motion of fluid substances such as liquids and gases. These equations state that changes in momentum of fluid particles depend only on the external pressure and internal viscous forces acting on the fluid. Thus, the Navier-Stokes equations describe the balance of forces acting at any given region of the fluid. The Navier-Stokes equations are differential equations which describe the motion of a fluid. Such equations establish relations among the rates of change of the variables of interest. For example, the Navier-Stokes equations for an ideal fluid with zero viscosity states that acceleration is proportional to the derivative of internal pressure. This means that solutions of the Navier-Stokes equations for a given physical problem must be sought with the help of calculus. In practical terms, only the simplest cases can be solved exactly in this way. These cases generally involve non-turbulent, steady flow in which the Reynolds number is small. For more complex situations, involving turbulence, such as global weather systems, aerodynamics, hydrodynamics and many more, solutions of the Navier-Stokes equations can currently only be found with the help of computers. This branch of science is called computational fluid dynamics. General form of the equation. The general form of the Cauchy momentum equation is, whereas the fluid density is the substantive derivative, is the flow velocity vector, is the specific body force vector, and is the stress tensor, unless the fluid is made up of spinning degrees of freedom like vortices, is a symmetric tensor. In Navier-Stokes equations, the stress tensor can be decomposed as whereas a static isotropic stress state, and is the deviatoric stress tensor, corresponding to the part of the stress due to the fluid motion. Generally, the scalar can be taken as the thermodynamic pressure, whereas is called the viscous stress tensor. Furthermore, the diagonal components of tensor are called normal stresses and the off-diagonal components are called shear stresses. The vectorial Cauchy equation above can be written then as this is actually a set of three equations, one per dimension. By themselves, these equations are not sufficient to produce a solution. However, adding other conservation laws and appropriate boundary conditions to the system of equations produces a solvable set of equations. The conservation of mass provides another equation relating the density and the flow velocity. On the other hand, the identification of with the thermodynamic pressure is usually possible. Therefore, a thermodynamic equation of state must be used to connect the pressure with the density and another state property, such as temperature or enthalpy. This in turn brings another unknown to the problem so that an equation for conservation of thermal energy must also be solved along with momentum in mass conservations. In the case of an incompressible fluid, there is no relationship between the pressure and the density. The Navier-Stokes equations and mass conservation are then sufficient to determine the solution to a fluid mechanics problem. Actually, the absolute pressure in an incompressible fluid is indeterminate, and only its gradient is relevant for the equations of motion. Taking the divergence of the Navier-Stokes equation and using the mass conservation equation to simplify the result gives a Poisson equation for the pressure. Additionally, in order to close the system of equations, a constitutive equation relating the viscous stress tensor to the velocity field must be introduced. This constitutive model, which depends on the nature of the fluid, is the basis for the distinction between Newtonian and non-Newtonian fluids. Newtonian versus non-Newtonian fluids. A Newtonian fluid is defined to be a fluid whose shear stress is linearly proportional to the velocity gradient in the direction perpendicular to the plane of shear. This definition means regardless of the forces acting on a fluid, it continues to flow. For example, water is a Newtonian fluid, because it continues to display fluid properties no matter how much it is stirred or mixed. A slightly less rigorous definition is that the drag of a small object being moved slowly through the fluid is proportional to the force applied to the object. Important fluids, like water as well as most gases, behave, to good approximation, as a Newtonian fluid under normal conditions on Earth. By contrast, stirring a non-Newtonian fluid can leave a hole behind. This will gradually fill up over time. This behavior is seen in materials such as pudding, oobleck, or sand. Alternatively, stirring a non-Newtonian fluid can cause the viscosity to decrease, so the fluid appears thinner. There are many types of non-Newtonian fluids, as they are defined to be something that fails to obey a particular property. For example, most fluids with long molecular chains can react in a non-Newtonian manner. equations for a Newtonian fluid. The constant of proportionality between the viscous stress tensor and the velocity gradient is known as the viscosity. A simple equation to describe incompressible Newtonian fluid behavior is whereas the shear stress exerted by the fluid is the fluid viscosity, a constant of proportionality is the velocity gradient perpendicular to the direction of shear. For a Newtonian fluid, the viscosity, by definition, depends only on temperature and pressure, not on the forces acting upon it. If the fluid is incompressible, the equation governing the viscous stress is whereas the shear stress on the face of the fluid element in the direction is the velocity in the direction is the direction coordinate. If the fluid is not incompressible, the general form for the viscous stress in a Newtonian fluid is whereas the second viscosity coefficient. If a fluid does not obey this relation, it is termed a non-Newtonian fluid, of which there are several types. Non-Newtonian fluids can be either plastic, Bingham plastic, pseudoplastic, dilatant, thixotropic, rheopectic, viscoelastic. In some applications, another rough broad division among fluids is made: ideal and non-ideal fluids. An ideal fluid is non-viscous and offers no resistance whatsoever to a shearing force. An ideal fluid really does not exist, but in some calculations, the assumption is justifiable. One example of this is the flow far from solid surfaces. In many cases, the viscous effects are concentrated near the solid boundaries, while in regions of the flow field far away from the boundaries, the viscous effects can be neglected and the fluid there is treated as it were inviscid. When the viscosity is neglected, the term containing the viscous stress tensor in the Navier-Stokes equation vanishes. The equation reduced in this form is called the Euler equation.